Hello everybody. In today's class, we are going to learn a little bit about MTI and pulse Doppler radar. Right? When we started this series on radars, in the first class, we learned about the radar range equation. Right? For a pulse radar, what would be the range equation? So that we saw. And in the second class, we talked about continuous wave radar, and we talked about a modulated CW radar, how we can use a modulated CW radar. CW stands for continuous wave. So how a modulated CW radar can be used to determine the range. And in the third class, we discussed about CW radar, unmodulated CW radar. Using unmodulated CW radar, we could find the velocity of the targets. Okay. Now what we are going to see is a pulsed radar. Okay, in which we have MTI and Doppler. So it is pulsed in nature, so we can find the range, and it is also a moving target indicator and a Doppler radar, and hence we can find the velocity also. Okay. So this is what in the first class we derived the equation for the radar maximum range. If you don't remember this, please refer to lecture number 1. And subsequently we discussed about modulated CW radar, wherein the transmitted wave was being continuously modulated. So it was not a fixed frequency that was being transmitted continuously. The transmitted signal was different, and then the received signal is shown out here in the blue dashes. So the difference between the received and the transmitted signal, that again we did the derivation. That different signal would be proportional to the range. If it is coming, the reflected wave is coming after traveling a larger distance, then obviously there will be larger frequency difference. So this we saw in the second class, right? And then in the third class, what we saw is we are continuously transmitting a frequency. Now this frequency is not modulated. This is a fixed frequency which is being transmitted continuously, and the received frequency would be the same if it is a stationary object, but if it is a moving object, that frequency would either move. If the object is coming towards the antenna, then you have a positive shift in frequency, and if it is moving away from the antenna, you have a negative shift. And hence you have this plus minus. But this FD, which is known as the Doppler shift, again we saw that FD is given by this equation, right? The amount of Doppler shift is proportional to the velocity. So Doppler frequency and the velocity of the target is related by this equation. FD is equal to 2VR by W. This again we saw in the third class. Okay, so today we are going to see something known as moving target indicators and pulse Doppler radar. Okay, so this is the block diagram. A pulse radar that utilizes the Doppler frequency shift as a means to discriminating moving targets with respect to the stationary targets is known as MTI and pulse Doppler. Both are the same. There is a small difference between these two, which I will discuss subsequently in one of the slides. Okay. First, let's assume it's same, and then there is a minor difference between these two that we will discuss. Essentially, it's a pulse radar. Using the normal pulse range equations, you find the range. Over and above that, along with the time which is noted between the transmitting and the received signal, which is used to compute the range, we also are going to measure the Doppler shift in the received signal, and based on that Doppler shift, we are going to say, okay, that it's a moving target or it's a fixed target. Okay, so essentially, if there are so many, the echoes from the stationary objects, they clutter the scope. Okay, they kind of can confuse the operator, right, with so many unnecessary blips on the scope. So the ATC controller or whatever is the system is there, if it's an onboard radar, you are not really bothered about stationary targets. We are more concerned of targets which are moving, right? So that is the reason we have to try and distinguish between the echoes received from stationary objects and that from a moving object. Now let's just consider this in a block diagram. We have a continuous wave oscillator. Initially in the CW block diagram, we saw that was being transmitted. Now we are not transmitting it as it is, okay, because we have a power amplifier in between, and that is switched on with a pulse modulator. So obviously you are transmitting in small pulses, okay. So if you are transmitting CW, then you require a large amount of power, right? Continuously you are transmitting large amount of power. So obviously one benefit you can straight away see here that not that much of power is being transmitted, okay. It's in pulse form, and also the pulse form enables us to compute the range also, okay. That we saw in the very first class, how pulse radars compute the range, okay. Now this received signal will have a Doppler component, okay. This Doppler component will be there only if the echo is from a moving target. Now if I try to write the equation, so this is the one which is being transmitted, okay. A1 is the one which is being transmitted, okay, not this, okay. And this A1 sin omega t is the frequency which is being transmitted out here. And now this reference signal is A2 sin 2 pi ft, okay. Ft stands for the transmitting frequency. Now the echo signal which is coming, which is being received by the receiving antenna, and will have some other magnitude. So magnitude doesn't matter here. So it will have 2 pi ft plus minus fd, okay. So there will be a Doppler shift, okay. And also because this wave has gone to the target and it has come, right, and whereas this signal is coming directly here, so by the time this has gone and here this signal has moved forward, right? So there will be a phase difference between these two signals. So the transmitted wave has to go hit the target and it has to come back. So the total distance traveled will be 2r. So the time taken, okay, for that travel will be 2r divided by c, right? So this is the total time. Now if I divide it by the time period, okay, of the waveform, so I'll get those many lambdas, because each time period is represents one lambda, right? So I can divide it by 2, or I can write 2r f, the frequency, okay, and then by c, right? This is the transmitting frequency. Now if I have to write it in phase, okay, so this is in lambda. So these many lambdas. So if I have to write it in phase, I can multiply it by another 2 pi. So I get this, right? So what do I see from this equation? So this is a very important equation. Now this is the received signal which I am getting, okay. There will be a Doppler component and there will be a phase shift. So this Doppler component induced FD is because of the relative velocity between the target and the antenna. Whereas this phase difference which gets induced, that is because of the distance r between the antenna and the target, okay. So that is r. So timing will assume that this is not a time varying thing, because sorry. So what happens for now? What we are going to do? This signal and this signal, we are going to beat it in the receiver and take out the beat frequency. Now, if I beat these two frequencies, right, it will like sine A into sine into sine. So one component will be ft. If you add these two, it will be 2 ft. That will be very high frequency. So once you employ a low pass filter, that gets filtered out, and one will be the difference of these two frequencies. So when you take the difference, these ft goes and only fd remains. So this is fd, and this phase shift which occurs because of the distance traveled by the wave, that is also. So this is what you get at the output of the receiver. Now let me remove all these unwanted things. Now if you observe this waveform, right, what happens for a stationary object. Okay, for a stationary object, there is no FD, right? So this vanishes off. So there is no this component, only this. Okay, so this is also a 2 4 pi ft rc, they are all constant. So I get a DC signal, okay, for a stationary target. Whereas if there is a relative motion between the target and the antenna, I have an FD signal. So I get a sinusoidal signal. So now I have an AC signal. So clearly, once I have this block diagram, okay, what I am doing is I am taking the frequency which is being transmitted, and I am taking the frequency, the signal which is being received. I am mixing up in a mixer of a receiver, and I am analyzing the output waveform, right? So this FD waveform, if you see here, this is the signal. Now, obviously, if FD is a function of the velocity also, like we learned in the CW radar in the previous class. But also what you can see is, if there is no relative motion, if FD is 0, then this whole thing becomes a constant. That means I get a DC output, whereas on the whereas if there is a relative motion, then it's an AC signal. So this philosophy is made use of in distinguishing between an stationary object and a moving object. Now this is a simple amplifier, but more often than not we use a super heterodyne structure, where the transmitted frequency is actually created by mixing a shallow frequency and a coherent frequency. I have a mixer which will add these two frequencies, FL plus FC, and that is being transmitted. So the received frequency will be FL, FC plus the Doppler shift, and then I have one more mixer, and then I have FL being mixed here. So FL they get cancelled. Now I just have FC plus or minus FD, and then in the second stage I do mix it with FC, then FC gets cancelled, I get FD. Now the advantage of doing it in two stages is this helps me in removing the image frequency, okay, whereas this helps me here, right, in selecting the in having a better selectivity. So you could refer to my lecture on communication systems, in which I have explained about super heterodyne receivers and the advantage of having like a super heterodyne structure, where you have an IF also, and downscaling the frequency in two steps. Okay, so in the first step it helps in removing the image frequency, and in the second step you can remove the you can have better selectivity. Okay, otherwise here you have to compromise. Okay, either the image frequency response will be poor if you have higher selectivity, or if you are targeting for better image selectivity, better image frequency rejection, then the selectivity will get hampered. Okay, so that's why we use a super heterodyne receiver. Okay. Now coming, this is now an A scope. A scope is, this is the range, right? Just if you keep plotting the range, so this is the waveform. This A, B, C, D, E, F is with respect to different time. Okay, T1, T2, T3. Okay, this is a combined, as you see from a human eye, and this is the scope from the which is coming from the electronic unit, and this is the final scope output. So if you see here, for all stationary objects, it's a DC signal. It doesn't change with time. So you will get an image like this. Whereas here, this is a moving target, and here also you have a moving target. So in the moving target, right, with each, like we saw the moving target. Okay, it is a function of, it's a sinusoidal signal, right? So and hence this it's not fixed, it's not at same value, so it keeps changing. So you will see an eye diagram here, right? So this way you can say, okay, I have a moving object here, I have a moving object here, right? So again, to make this thing even much easier to interpret, we can have an MTI cancellers. Okay, like we first see how a two pulse canceller works. So I have a received signal, so I have a delay line. Okay, so this has to delay the signal by t. T by time t, which is 1 by PRF. Okay, so pulse repetition frequency, this stands for pulse rep, and then you subtract the signal. Okay, and then you have a full wave rectifier, because we are not bothered about whether it is positive or negative here. Okay, so we can rectify this. We just want a good blip out here, right? So this negative thing, we don't want this positive negative here. Right, so what we are doing is we are delaying it by one time period. So if this is the first signal and this is the second signal, here we have a moving indicator, moving target. Here also we have a moving target, but here these are the echoes coming from the stationary targets. So if you subtract this, okay, after a delay, all these things gets cancelled. Only where in those places where you have a moving target, okay, they don't get cancelled totally, because they are time varying signals, and hence you will get a blip only at the so if you have a rectifier, and you will get a positive blip here. You will get a positive blip here, right? So only where there is a target with moving targets is detected. Okay, so this is how you can remove all the clutters from your scope, right? So this is how it is done. Now if you see, now there is an other issue, some small issue known as blind speed. Okay, let's try and understand that what it is. So let's discuss about the filter characteristics of a delay line. So this is the a signal which is received, right? K, some amplitude, sine 2 pi fd. Fd is because of the Doppler shift, right, of the because of the relative velocity between the target and the antenna. So Fd is the Doppler shift. This is because of the distance between the target and the antenna, right? So now you are taking excuse me. Now this is the signal. V2 is the signal after a delay or one cycle prior. Excuse me. So V2 is a signal which is from here, right? The delayed signal. So one PRF and one time period and before that signal. Okay, if you see that, so minus t, right, and then the phase remains constant, right, and the Doppler this also remains same. Only difference is from here to here. Okay, the signal is delayed by a time period t, because I have an delay element here. So now if I subtract these two, right, again sin A minus sin B, if I do that, here I am doing sin A minus sin B, I am not multiplying these two signals, I am just taking a plain subtraction of these two signals, and if I use that in a mathematical formula of sin A minus sin B, I get this result. Now if you look carefully at this, right, this is a sinusoidal signal, right, okay, with a frequency of fd, right, and what is this? Okay, this is not a time varying thing. This defines the magnitude of that signal. Okay, so 2 pi fd and t. So now if I plot fd on the x-axis, and if I plot the amplitude, okay, so this is a sinusoidal signal. I am not worried about this. I am only talking about the magnitude aspect out here, right? So this is fd. So when fd is 0, that means if there is no Doppler shift, okay, so I don't get a DC signal. That is fine. Okay, that is known, and that is what in our design initially we said this is how it is going to help us remove the static target echoes from the static target. But as fd increases, okay, why will fd increase? As the velocity increases. Okay, as the velocity increases and fd reaches a value 1 by 2 pi 2t, right? What is t? T is the right t what is the capital T? T is 1 by pulse repetition frequency. Pulse repetition frequency 1 by PRF. Okay, now when it reaches this value, I will have a max amplitude. I'm just talking about this particular term, right? And then when FD reaches 1 by T, okay, this becomes 0. Okay, what does it mean? That means as the velocity of the target increases, okay, this output signal which is available here, right, or here, okay, it increases and then it comes to zero. Again it increases, it comes to zero. So these are known as the blind speeds. Okay, at these speeds, okay, at these speeds, although there is a Doppler shift and Doppler frequency is there, in spite of that, because of this particular circuit which we have employed, the output would be a zero. So these at these speeds, okay, the radar, I will not have a signal out here, right? Right, so these signals will not be available at certain speeds of the target. And what are those speeds? Those speeds are represented here, okay, where FD is equal to this, right, at these values. So now FD is equal to N by T, where N is an integer, 1, 2, 3, 4, right? So T I can write it as FP, or the pulse repetition frequency. Right, so whenever the Doppler frequency is a multiple of the pulse repetition frequency, at those speeds, okay, it will not be visible. Okay, the output won't be there, so we are likely to miss the targets. Okay, now we know the relation between the Doppler frequency and the velocity of the target. This we saw, right? VR is the relative velocity of relative velocity is there, but right now we can say velocity of the target because the antenna is static. So VR. So if I from the if I have to find out in a VR, right? So the blind speeds, okay. Lambda FD divided by 2. So lambda FD divided by 2, and this FD, if I replace this as NFP, right? So NFP, so I get this, right? So at these velocities, where N is equal to 1, 2, 3, 4, I won't see any blip on the scope, right? So the MTI will fail to detect the moving target at these velocities, okay, different velocities, N is equal to 1, 2, 3, 4. So this is known as a blind speed. So this is one of the limitations of the MTI pulse radar. But what is the advantage? There are two advantages. One, you can find out the range also, unlike a pure CW radar where it only finds the velocity. Here you can find the range also. Second is on the power aspect. You are not continuously transmitting a large amount of power, right? You are only sending the pulse, small power. You are transmitting power in small pulse. So that's the two advantages. Okay. Only thing is, this is a blind. Another important thing, a very important thing from this equation is, right, it is desirable to have pulse repetition frequency very high. So if you have the pulse repetition very high, then the blind speeds will be like suppose if I have a very large pulse repetition frequency, say I am missing out on a 1 max speed or 2 max speed, 3 max speed, like that, right? If I have an lesser pulse repetition frequency, or then say a 0.5 Mach and a 1 Mach, 1.5 Mach, 2 Mach, so I'll miss out lot many frequencies. So as far as if I want to eliminate blind speeds, okay, so what is that I can do? I have to increase the pulse repetition frequency, okay. But like in the when we discussed in the very first class, right, this is the PRF, right? I have transmitted a pulse, I have received a signal, I have transmitted the second pulse, and I have received the second reflection from here, okay, this received pulse. Now if the target is at a very large distance, okay, if I am transmitting a pulse here, it is going to reach here, right? So if it is going to reach here, then it will be computed wrongly, right? So this distance it will be computed. Now, so for large range, what do I have to do? I have to have this pulse coming somewhere here, right? So a range, for max range, I should have a low PRF, right? So that is what. Now here I am saying for blind speeds I should have a high PRF. for a range I should have a low PRF. So there is a trade-off. So that is where the only difference between MTI and pulse Doppler comes in, right? So in MTI we use a low PRF, okay, and since we are using a low PRF, right, so there is no ambiguity in Doppler measurement, right? So no, there is an ambiguity in the Doppler measurement, so blind speeds will be there, okay, because it's low PRF, right? But then the range measurement is very good, right? Whereas in the pulsed radar I am going to use high PRF, okay. The block diagram, everything remains same, right? Only the choice of PRF is different. So if I use an high PRF, okay, then there will be a range measurement, so the total max range, okay, becomes a difficult thing. Second time echoes can cause wrong, can give ambiguous range measurements, right? But then the blind speeds will be higher, okay. So this is the only difference between an MTI and an pulse Doppler radar, okay. Now instead of having only one delay line canceller, I can have a multiple, like I can have either like this or I can have this. So if you see here at these frequencies, right, where these are my frequencies, Doppler shift frequencies corresponding to the blind speeds. So if you see here and the clutter here, this is the clutter. So you see if you are using this multiple stages, this is the dotted line, all right. So and this is after the double cancellation. So in the double cancellation you will find that the clutter elimination is better, right? So if you use multiple stages like this, we will be able to suppress the clutters around the these blind zones in a much better manner, okay. So that's why generally there we use more than one. We don't use single line cancellers, but multiple line cancellers are used in practice, okay. Now we saw that, okay, these are the blind speeds if you use a particular pulse repetition frequency, right? What if I change the frequency, then this is the one, right? So this blind speed is here, and this blind speed is here, so they're not matching. So these blind speeds are a function of right the frequency, right? The pulse repetition frequency. Similarly, this is coming here, right? So what if I use multiple or staggered PRF? That means I use I don't transmit pulses at the same PRF, okay. I can transmit here, here, and then here, and then here. I use a multiple PRF or more than one pulse repetition frequency, mix and match. Now if you see here, then this will be detected by this PRF, right? So the blind speeds will be pushed forward by the LCM factor, right? So now this is 4T1 and 5T1. So the first blind speed will be encountered here when this condition is met. So we are able to push the blind speed from here and here to here, right? So whenever this condition is met, then the first blind speed will be encountered. So this is the response, total response. So if you see here, so by using multiple or staggered PRF, multiple PRF or staggered PRF, right? So both the conditions have to be met. This condition also has to be met. This condition also has to be met only for those velocities. Okay, you will have a set of velocities here. You have a set of velocities here. So whenever both those velocities are matching, right? So if you say if you go back this equation, right? So there will be two set of velocities, one given by one PRF, second given by the second PRF, and when those velocities match, okay, only then you will have the blind speed. So you can take the LCM of both of them, right? So you will get, and blind speed will be pushed very farther ahead. So that way we can improve that particular aspect, okay. Now if you keep this things closer to each other, right? So suppose right, one is at 4 megahertz and 5 megahertz. Obviously 20 megahertz and something corresponding to that will be the right correspond. If you take the LCM between 4 and 5, let me put it that way. Right, if I take an LCM of 4 and 5, then I am going to it will be around 20. Now if I try to take between 4 and say 4.1 and all, it might be somewhere close to 36 or something like that, right? So that means if you have these two PRFs close to each other, right? If you have close to each other, then your blind speed actually will be very, very large, right? So it is a very good thing. But the only problem in having close PRFs in the multiple PRF configuration, the thing is this nulls which are coming, okay, they will come down and down, right? And if it is down, then this could pass through the band pass filter. In the next stage, we will have a band pass filter, right? So this this may not be passed by the band pass filter if this null is coming close to 0. So there is a trade-off, right? So if you keep very close to each other, then these dips will come closer. If you keep this very, very far away, then you will get these nulls which are coming there will be it will be relatively much more than the 0 level, and hence the probability of missing that will be lesser. Okay, so that compromise you have to do, right? And this is the last thing in the Doppler in today's class. This is known as range gated Doppler filters. Okay, now we have Doppler filters, right? So Doppler filters are nothing but a pass band filter, right? If I see the block diagram out here initially here, right? So I have an FD. So this is actually this receiver will have an mixer and a band pass filter, right? So the band pass filter will remove the DC component and also the high frequency components. High frequency components, because when you mix these two, you have two FT also. You don't want. So this is actually a band pass filter, right? So if you see the band pass filter in the frequency domain, right? So this is how it looks like, and in the time domain, this becomes like this, right? So what does it indicate? So when these pulses are received by this band pass filters, they are going to spread in the time domain, right? But in the like we said, this is a pulse radar, and we are also computing the range. Okay, so if the signal which is received here is going to have a ringing effect, and it is going to produce noise in the time domain, then my range computation will get affected, right? So that is not a desirable thing. So what I do have generally in the MTI, I can have some range gates. Okay, so these gates will be opened up for a duration equal to the pulse width of the transmitting signal, but as per the range only, right? So for the closest range, gate will be opened first, and then this and this. So by this and then we are selecting the signal only from the corresponding path. So that way, whatever ringing is induced in all these things, they are not affected in the next range determination circuit. Okay, so that is known as range gated Doppler filters. Okay, so with that we come to an end of today's class. In the next class, we are going to talk about electronic warfare. Okay, thanks a lot.